for attending. My name is Suhas Kulkarni. I'm a VP of Engineering and also lead architect at GRE International. I'm responsible for looking after the company technology strategy and future-proofing our tech stack to meet the demands of our growing business for the next 4 to 5 years. And with me co-presenting is Kandarp Shah, who led the team in building the data platform for GRE. And we have some really good information for all of you. You can take it back and solve your business problems. And the talk outline today is mobile game analytics as a use case, how we built our platform to address this use case, and some of the decisions we took, mistakes we made, and also challenges we faced along the way. Kind of give you a good feel for what it meant for us to build the platform, and then we'll go deeper into the new analytics architecture, leveraging AWS tech, something that helped us solve our business problems. And at the end, the lessons we learned. It's the best practice, I would call, something that you can take back. But before that, quick poll, how many of you are from gaming space? Wow, great. How about the console? And, okay. Free-to-play mobile gaming? Awesome. How about B2C space, consumer-facing business? And B2B? Okay, this looks like good distribution. So I think today's discussion will definitely, kind of applies to all of you, and especially mobile gaming, where we are going to discuss more deeply. So before that, who we are a global gaming company with 1,800 employees worldwide. We have our studio in Tokyo, San Francisco, and Vancouver. And our games are played in 6 different continents. And 13 of the games are produced in North America. And Knights and Dragons, for example, was the top 10 grossing in 41 countries. And also Crime City, which is in the RPG genre, was top 10 grossing in 140 countries. We focus on 3 different genres: casino, RPG, and strategy. There will be more to be added to the portfolio. So that's who we are. I will jump into success factors in gaming, what it means to launch successful games. Some of the key ingredients are you have to have great storyline, great gameplay, and then you have to have great mechanics. And with that, you also need good content. So we are all about entertaining users. So to bring all that, you have to have great content, gameplay, and mechanics. So with that combination of that, you can effectively engage your audience, and that will mean your retention of those users will be pretty, very good. And there is a strong correlation between retention and your monetization. So along the way, you hope to generate more of those microtransactions within the game that will, improve your game performance. So the key thing is you have to continuously keep adding the content. You should never be in a situation where players run out of content, and that's the key thing. So with all that, you would, game producers, they launch the game, it goes live, there's a marketing spend behind it. It does fine for the first few months, and suddenly, the game's metrics are no longer, they're not the same as at the time of launch. Why is that? And there are a lot of different things that come into play. So it's a great game, but I know it was working fine, but why it is not working? Also, similar scenario is when a gaming company acquires another one, and which worked well. After the acquisition, for some reason it does not work. Again, you go back to those questions. Why? Why not? Why KPIs are not looking that good? and why is my game not successful anymore? So as a game producer, you'd have to ask these questions. Oops, sorry. Okay, why is game not performing well? Why players are no longer spending, and why is the retention metric is so poor? And how can you change that around? How do you improve your ARPDAU, average revenue per DAU, and how can I increase the percentage spenders within your game? Again, that's again is dependent on your user retention. So to answer all of that, you need game analytics and insights. That's really one of the bases. Although there are success factors for gaming, but in addition to that, you have to have game analytics and insight as a complement for the long-term success of your games. So we set out to build analytics platform in-house, and at Gree, we have a very data-driven culture. All of our game designers, producers are completely data-driven for making some of the very important business decisions to optimize the game design. Also, how effectively are we spending our marketing money? And it's all about, if you think about secret of gaming, no longer a secret, but it's all about acquiring high-quality users and then retaining them for a longer period of time and then monetize those users. And at the same time, entertain them. That's really what it takes to produce great games. And again, if you look at to optimize game design, to optimize your marketing spend, you have to collect all that key information. And so on the client side, we capture a lot of game events, things like player login, tutorial completion, your battle fight that's going on within your game, and if it's a casino or slots game, all the UI, all the spin events and things like that. So a lot of events are captured. Also, from a player experience point of view, you have to know, is the game crashing? What's your percentage crash? What's the stability of your game? So that's on the performance of the game and with respect to player experience. And things like how many users are playing during a day, how many sessions and things like that. So all of that information is captured from your clients, mobile clients. And then on the user acquisition side, it's all about knowing, building a campaign performance where you have to know the users that you acquired. These are the money you spend to acquire users. How are they doing within the game? What's their player behavior? Are they spending more than what we paid for? So it's all about LTV, lifetime value of the game, versus the amount of money you spend to acquire that user. So that's where campaign performance is super important for optimizing your marketing spend. And also we collect ad clicks, downloads, and a ton of other information, impressions, from each of the ad network we rely on to acquire these users. So again, you want to spend on ad network that is bringing high quality users. Quality of users doesn't have to be in terms of revenue, but it also means how active are the users within your game. So quality can be different for different people within the organization. So attribution, you also want to credit the ad networks that actually brought those users. There should not be any duplication between ad networks claiming that these users came from me versus the other ad network. On the engagement side, it's all about player targeting. How can you convert non-spenders into spenders? How can you recognize the inactive players? What kind of action can you take? Again, that's all. You need a segmentation tool, for example, to identify and target those key users. And we also collect events like IAP, in-app purchases, soft currency balance, hard currency balance, and so on and so forth. So as you can see, a lot of information is captured. from a data collection, if I were to summarize, so you have events coming from your mobile devices, Android, iOS, and game servers. There's a distinction. We collect high-value events on the game server side. Low-value, high-volume kind of events originate from the mobile devices, from the client side. So there's a reason for that. All the IAP, your purchase events, player login events, these drive key performance indicators, and based on which you make your business decisions. So those have to be accurate and reliable. There's a good chance you may lose events on the client side, and although we have built SDKs to ensure offline events get eventually sent over to our backend systems. And ad networks, that's the other area where we collect a lot of information. So you can see there's a lot of things, a lot of information gathering happening within the game or in the game ecosystem. And quickly looking at the data size and growth, each event that comes to the analytics platform is about 1 kilobyte. And we collect about 500 million events per day. Comes to around 500 gig. On certain weekends, certain events, live ops events, this can actually spike up. So this could go up to 1 terabyte for that given day. Although it is not big data scale by any means, but over the lifetime of the game, you are really working with a petabyte scale of data in your system. And again, if you multiply that with number of game titles you are producing, it's order of magnitude size. And it's a JSON format. Looking at the database schema, how we organize, how we store data, every game that we produce has its own database schema. And that's where your game designers and the BI analysts or the data scientists within the organization decide, what kind of events you want to capture, whether it is about player behavior, whether it's about the game performance, about how can we optimize game design and things like that. So based on that, every game event within a game is a table for us, and then highly denormalized structure, very schema aware. So there are about 40 to 50 tables or events that are generated for each of the game. And roughly, if you have about 20 different titles, it comes down to 1,000 tables within your data warehouse. So as we add more game titles, that's only going to increase. So that's the kind of a database schema. So as you can see, we are collecting information, as number of games are produced, or when your games become big hit, we need a system that can collect all of this information, process it, and store it in your backend database. So that's really the primary requirement for us. And so we need a data collection and streaming to database. That's the capability we need. It also should be, there should be zero data loss or zero data corruption. These two requirements are super important because you want your users to trust your data. If there is a data loss, your metrics are skewed, and there is no way you can trust that data or make your business decisions. So credibility is everything whenever it comes to your data platforms, and that's the number one goal for our platform. And of course, guaranteed data delivery is also important. Data delay is fine as long as it makes it through. So those are the key requirements. I want to talk about briefly about some of the architectures or platforms that we built initially, and then look at the new one later on. So initially, we started off with our Generation 1 analytics platform. Usually, if you look at any gaming company, if you produce the first game, it's likely that analytics is an afterthought. And so we were also in the same boat. We had one engineer working on, built a LAMP stack, and it was a sharded MySQL database, and all the game logic and as well as analytics, logging and loading of data was happening in the same logic. So although we decoupled those two processes, but what we quickly found out was as our game became popular, more events started coming in. We were just unable to keep up with the incoming data rate. So it was not scalable. So we quickly realized that within a few weeks of putting this into production. So we decided to go next generation. We relied on Flume and also had an MPP data warehouse. At the time, it was the right call, but during those times, Flume was a project in infancy. It was very immature, and we also did not have deep understanding of Flume. And with limited engineering resources, we thought we knew everything about Flume. There were 3 problems we ran into on the Flume side. One was we enabled this feature of Flume called reliable delivery mechanism, which guarantees data delivery to your data warehouse. So what ended up happening was due to network latency and also the timeout, tuning of that. It's based on an ACK system where agents would look for the acknowledgement that data has been delivered. If it does not see it, depending on your network latency, it will try to resend that to the collectors. And so what that meant was, we were duplicating data in our data warehouse. So we were constantly in the business of deduplicating data in our data warehouse. And so that was one. And we also did not have good monitoring, process control, and alerts set up. Thinking back, I wish we had those, but some of these agents would go down without our knowledge, and the disk would fill up, affecting our overall game performance as well. So that's the second one. And the plugins that we developed on the collector side to load data, it was not optimized enough that, again, it was not keeping up with the inflow of data. So the overall ETL speed was slow. So again, just because we did not have deep understanding of Flume and did not have enough resources to invest into maintaining the system, we decided we need a system that we can manage ourselves, something that is under our control. So what we then did was built a relay engine, which replaced the Flume, very simple in its design, and it was scalable too. All it is you have these senders which would collect all of your analytics logs, send it to listeners, and you can scale listeners based on a number of events. And these listeners would log them again locally, and then another process would pick up those log files and send it to the next stage, which is replicator. Again, replicator would replicate your log files based on the syncs and number of consumers you had. And then you had copiers which would collect that and load them into database. And we also had a consumer that would go to S3, so all the raw logs would go there. And there were times when, due to data issues, we had to constantly go back to raw logs, reprocess them, load them again. And there were some other use cases that came out, was to BI team decided, hey, we need our own dedicated cluster, so which meant we had to have one more data warehouse sync. And that was one. Then there was another use case where we need to monitor certain KPIs real time. And so we had like 4 or 5 consumers, and the replicator was doing mindless I/O, a lot of replication, and there is no compression. We didn't have enough time to really invest into this tech. And although it was scaling well, but maintenance-wise, it was quite high. So we abandoned that. And so challenges we faced, hard to maintain and scale. Spike in live ops events would slow down some of the high-value events that we were processing. And it's adding a new sync was difficult. And anytime we do writes to data warehouse, it affected the query performance for BI users. So while you're loading data, someone is querying, And if you think about if someone is running a long-running transaction or query, it will bring down all of your processing. So again, there is a data latency introduced in your system. And so those are some of the challenges we faced. So again, going back to original requirements and going through 3 different architectures of different platforms, we added a few more requirements based on what we learned. We need near real-time data latency and ability to do real-time ad hoc analysis and ease of adding consumers. And the last one is very important, which is managed service. We did not want to manage these platforms ourselves. We are in the business of making games. And the time it takes or the resource you have to invest in making your analytics platform highly resilient and reliable, it takes a lot of energy out of our business. So that was a clear goal for us, something that we, at the time we saw AWS came up with great technology components we can directly put into our stack and then make it highly resilient. So then we decided to take on, adopt all of the AWS stack and make it, completely managed service. So that was something that I wish we had done in the past, but in the end, we knew we were on the right track. So with that, I would like to introduce Kandarp Shah, who led the team in adopting this technology and making it production ready. And he actually did, entire team did that in record time, migrating to Redshift as well as, adopting Kinesis. So, Kandarp.
Thanks, Suhas. So when we starting out with the new analytics architecture, we set up pretty clear requirement that what we want to achieve from this architecture. So keeping those requirements in mind, we wanted to start building out simple. So we started with ingesting the data, storing that data, and then analyzing that data. So now for ingestion, you can either use some of the open source technologies like Kafka, Flume, or Scribe, or you can create your own REST server. But in that case, you have to manage your own cluster and then deal with some of the scalability issues. So we decided to go with the Kinesis for ingestion of data. For storing, we are using Amazon S3 for permanent archival of the storage. And we are using Redshift, so we can run any ad hoc analysis on top of our data. So with that said, I'm going to walk through each components of this simple store data pipeline. We have producer, sender, consumer, and the loader. And if you look at the producer, we have all of the game services developed using either PHP or Python. And whenever these game services get called, we generate a few metrics. It can be player login event, or it can be a level up event. Apart from that, we also generate data on the client side, and those data get forwarded to analytics servers using SDK. In terms of the data, we decided to use schema-aware format from the beginning. So we use a JSON format, and that helped us using different tools for processing our data. So each event, apart from each record, basically has event-specific data, and in addition to that, it also has some metadata that we use for each event. It has game name, what is the event called, then it has some unique ID, and time when that event occurred. So we use those metadata for process that event further into the pipeline. And this is another example of the event we have. It's a battle fight event. And all of those events goes to a local file into the same server. And that analytics files get rotated every 30 seconds. So we decouple the process of sending data from producing data, and that helped us a lot along the way. So Kinesis Sender. So what Sender does, like it's sitting on each web server, and each web server is running this process in a background, and it performs several tasks. It connects to Kinesis and get the list of the shards we have. Then it's constantly listening to the analytics files that we are creating on the local machine. Those files are given to a specific worker within the Sender. So let's say, for example, this particular worker is given like 2 analytics files to process with. It's going to read file line by line and going to create a buffer of those data. So Kinesis has a put record limit of 50 kilobytes. So we keep building the buffer till we reach that limit. And that 50 KB is like compressed data limit. So we are compressing data as well. So once we reach that limit, we compress that data and then send that data to Kinesis using put record call. So this is a simplified version of like what Sender looks like. And this data goes to like each shard in a round robin fashion for this particular stream. So some of the design choices we made while building this Sender, should we use like single stream or we should use like game stream per game? Managing a single stream would be like much easier than managing a stream per game. We had like 20 plus games, and if we have to manage 20 plus game, it might have like taken much more resources. So we choose to go ahead with a single stream, and processing from a single stream itself was like fast enough in our case. So that worked out very well. Should I batch event or should I just send event as I'm generating? So in our case, like our record size is like hardly 1 kilobyte. So we decided to batch those events so we can like send more data in a single call. We are also compressing the data, so that allowed us to like send 4 to 5 times data compared to like if we haven't compressed that data. And there are cases when our event size is more than 50 kilobyte. So in that case, like if we compress data, we can still use the same pipeline to send those kind of events. Like one of the example is like crash log event, which is usually like between 24 kilobyte to 200 kilobyte. So compression allowed us to like send the same event through the Kinesis pipeline. Partition key versus explicit hash key. We are using explicit hash key, so we can like distribute load evenly across each shard. If you have like, if you are running an application exclusively for doing aggregations, partition key would be a better option. So as we are storing all of our analytics data into our local files, it is very important that we get the deployment process right. Otherwise, like if the server comes up and there is no Sender running on that particular machine, then you'll start filling up that disk. And at the same time, like if the server is going away and there is some data still left on the server, you will be losing those data. So we use AMI for each of our game groups. So each game has like its own AMI defined, and we constantly update this AMI, Amazon machine image. And each group is also like auto-scaled. So whenever like instance comes up, we create instance using AMI. And so this AMI has Sender already built in. Whenever we need to update a Sender, we deploy out to S3 object, and from S3, like it goes to AMI. And so let's say in this case, like when we are adding a new instance in that particular group, we put that particular server into a wait state, so we can like do we can perform some user actions. As AMI can be out of date, and there might be some deployments that you did after that, after building that AMI. So we want to make sure that we update all the application before we can put that into a production. So we do a puppet run before we put that server into production. And that puppet run takes care of like updating any software that needs to be updated. And after that finishes, we do several checks, and that checks, if it passes that checks, we put that server into proceed state, and from that it goes to like in service. So now you can see like we have 2 servers running into this particular group, and it's healthy and receiving traffic and also sending data to the next further into the pipeline. So when the server is going away, we use the same hooks, another hooks that AWS provides. So we put it in a terminating wait state, and then we do some checks and make sure that we send all the analytics files that we have to further into the pipeline. And if any logs that we need to back up, we do those as well at that time. And once we are done with that, we put it in a proceed state. So from there, it goes to, it terminated, and then we back to our one server auto-scaling group. So this is our deployment process look like. As we are also using EBS for our data volume, we could also like look for an EBS instance that has some data that not yet sent, and we can attach that EBS volume and then send that data to further into the pipeline. So consumer. So this is a simple store consumer which takes care of like storing data into S3. So this is our Amazon Kinesis stream. So we have this consumer using KCL library, and KCL library takes care of like communicating with the shards and making sure you have like enough workers processing each shards. It also does checkpointing for you. So it makes development really fast. So we are using KCL for consumers. So in this case, like we are running 2 consumer, and consumer is auto-scaled as well. So if your consumer is doing some CPU heavy processing and it's lagging behind, it's going to add more consumers as well. And instead of running like 2 workers on the same box, that will like, it will be running like one worker per machine. So from there, so KCL also provides you record interface, which emits record data, and so you can. So we take that record and also we are compressing data when we send data to Kinesis. We decompress that data, and after we do a decompression, we do some check for duplicates. The reason we are doing a duplicate check here is because when you send data to Kinesis, it might be possible that you are receiving HTTP 500 response type. And if you receive HTTP 500, you don't know whether data already made it to the Kinesis or not. So in that case, you have to retry that. And if you do a retry and your first call already made it to Kinesis, then you will be like duplicating that data into Kinesis. So this is something that we didn't find out like when we started building up this consumer application, but after realizing that we are getting duplicates, we find out that it's because of the HTTP 500 that we are retrying for put record calls. So once we do this duplicate check, we divide that data into a target table. And as we are sending all the events to a single stream, we need to make sure that we are buffering into the right, we are buffering right. Then after we divide it to target table, we do some simple validation for that particular data, and this validation happens based on like schema in Redshift. Then we do transformation for that data, and we do a transformation to like DSP, delimited separated format, and just to make sure that we are preparing that data for load into Redshift. So that DSP formatted data, we buffer it again. We check for a certain size, or if the timeout kicks in, we compress that data, and then that data goes to S3. So at the same time, we also send data to like RDS instance, which is just some kind of metadata information for S3 object that we are creating. And that helps us basically in loading process for Redshift. and we store like file name, what is the name of the game, and table name, then how many records within that particular file, and like what is the file size. So we store those kind of data, and that's going to help us into loading process. So now, loading data into Redshift. So we use that metadata information to load data. Whenever we need to load data into Redshift, we query this table, and then we get list of events that we need to load. Once we get that list of events, we get like what are the files that I need to load for this particular event. And once we get that, we start a transaction. We create a manifest file, which is just a list of files that we want to load from S3. After that, we execute a copy command on a Redshift using that manifest file. And Redshift gets data from S3 because we are storing data into S3. So it gets data from S3, and then we update status of that particular copy statement back to the process. And after that, once that is done, we do another copy command in the same transaction, and we do like batch of those copy commands into same transaction. The reason we are doing it this way because as Suhas mentioned before, that we have like 1,000+ tables in our data warehouse, and if we had to do it single copy commit for 1,000+ tables, it was taking a long time. So after talking with like AWS support team, we find out that if we, instead of doing a single copy commit, if we do a batch copy commit, it would help us a lot. And after switching it to batch copy, we actually got 50% gain in our loading time. So before it used to take like 8 hours, and now we bring it down to like 4 hours. And so after we commit that transaction, we update status back to a metadata DB. So next time when we run loading process, we know like what files need to be loaded. So this is like everything together for a simple store architecture that we have. So game server sending data to Kinesis, consumer receiving data from Kinesis, and then consumer uploading that delimited separated format into S3, and from S3, data goes to Redshift. Apart from the DSV, we also store another format, JSON format, that goes to S3 as well. And we store S3 format, we store JSON format specifically so we can run EMR job on top of that data. And there are a few use cases that we run EMR jobs on JSON data on S3. We calculate session length for each player, each gameplay, and we do it using EMR jobs on top of JSON data. So if you know about Redshift, you might wonder like why we need to use like two separate formats like DSV and JSON. We could have just, as Redshift supports a JSON format for loading data, we could have just used that format for loading data into Redshift. So we choose to use DSV for two reasons. Like we can minimize the network I/O, and that way like it's basically it can load data faster. And for some reason, if as our client are not schema aware, they might send some extra column which is not yet in a Redshift. So in that case, if we use JSON format for that particular data, it will just silently ignored, and so we will be missing that column. But if we use DSV format, we know that it's going to be rejected by Redshift, and we can rerun the process after fixing the schema into Redshift. So that's the reason we are using like two different formats for loading process. So there was a simple store consumer. Apart from simple store consumer, we also have like another consumer for calculating real-time aggregates. And so this consumer getting data from Kinesis, it gets the config file, which basically says that what are the metrics I want to keep track of. and it has also like time interval in that config file, and based on that, it keep calculating data from in memory for that time interval, and at the end of the time interval, that data goes to DynamoDB table. And we have stats dashboard that's using those data so any business user can like see in real time like what's happening within the game. So that was the real-time aggregates. We also have another consumer for a Spark cluster that we are running. Now Spark is really good at processing large amount of data, and it can run any MapReduce kind of jobs similar to Hadoop or faster than Hadoop. If the data is in memory, you can like run jobs like 100 times faster than Hadoop. So we are using Spark. So we have this Spark cluster, which is running Kinesis streaming library, and this library takes care of in terms of running KCL, and then it gets data from Kinesis. And you can specify like batch interval in which you want to load data into Spark. So we are using 5-minute batch interval. So library keep getting data from Kinesis, and then at the end of the batch interval, like it loads data into Spark specific data set, which is called RDD, and from RDD we convert that RDD into schema RDD. The reason we are doing schema RDD because our end goal for Spark right now is to be able to like query SQL, to be able to like use SQL queries. So if we do a schema RDD, it's a schema-aware format, and you can run any SQL or Hive query on top of that data. So we use Spark SQL, and Spark also provides like JDBC server that you can use to get interface for running any SQL statement. So this is our final architecture look like with all the consumers. So we have like consumer running for a Spark cluster and JDBC server for SQL interface. Then there is a consumer for real-time aggregates, and there is a consumer for uploading data to S3. So this is how it looks like with 3 consumers running right now. And so some of the lessons we learned during this process is for a sender side, like it's always good to decouple your data generation from sending. So in case like it allows you to like optimize your data send. So in our case, like we are batching, compressing data, and also like for some reason like third-party service that you are using is not is down or it's having more latency. You can back it up and then without affecting your real web service performance. Do a batch and compression whenever you can. That will allow you to like send more data within a single call. Put record HTTP 500 can result in duplicate. That's something that we learned after building a consumer. I would also recommend like monitor provision throughput exceeded exception that can help you like notifying about additional stream capacity required for your stream. So if you like start getting these exceptions like a lot frequently, that means like your sender is not able to like send all the data it's generating. So the lessons we learned for consumer side, use KCL whenever possible. It makes communicating with the shards and resharding very easy. Auto-scale your consumer group, so and monitor the load constantly on that one, so you can like add more stream capacity as needed. And in overall, like provision enough shards ahead of time, so it can take any picks in your data. Handle shutdown gracefully. So any producer or sender application, any sender or consumer application should handle like shutdown gracefully, and by committing any checkpoint that it needs to. So that way you are not duplicating data. and follow AWS best practices for any error retries and exponential backoff. So some of the takeaways from the talk. Kinesis makes data available for processing within few seconds. So you can build real-time application using it. It has a robust API. It provides various library, KCL, and connector libraries. There is also resharding libraries that you can use now. And it's very important to test your application logic by resharding your stream. So you know how it behaves when you reshard your stream. In overall, AWS is managed services. It's very scalable. It's cost-effective, and you can get up and running using any AWS services very quickly. So in our case, we built this data pipeline in just 4 months, starting from scratch, understanding what it provides, and then building prototype, testing it, and then making it production ready. It only took 4 months with 3 engineers and ops support. Cool. Thanks, everyone. That was it.